Good evening, everyone. The paper which we have chosen is Design of Zigbee-based wireless stepper motor controller using FPGA. And my group mates are Aniket Dhote and Abhinav Singh. So these are the contexts of our PPT. And I would like to introduce the flow of this paper. A wireless stepper motor controller is designed and developed in this article using Altera field programmable gate array, which is Spartan 3. In order to rotate the motor through the desired angle, speed, and direction, pulse width modulation is used. The stepper motor controller can be control can be done at three specific points, which is angle, direction, speed. It is performed using stepper motor driver, which is achieved with the help of following components. So these components are Zigbee. Zigbee is a communication module which has standard and able to create a personal area network using radio frequency, where stepper motor are multi-phase motor used in variety of applications. More importantly, every step is proportional to number of pulse provided. So it has better positioning, precision, and good for repetitive action in automation industry, where FPGA is an integrated circuit that consists of internal hardware blocks with user programmable interconnections to customize the operation for the specific application, where PWM is used to rotate the motor through the desired angle, speed, and direction. And the major role played by the UART is receiver transmitter is a computer hardware device which is used for asynchronous serial communication in data format. Further methodology is explained by Abhinav.
So I will be talking about how the author went about this project. So to power up the board which contains the FPGA, that is the Development and Education Board, a voltage regulator was used, which converted 9 volts to 3.3 volts. For the sensor, XB and stepper motor, it was powered by the LM7805, which stepped down the voltage to 5 volts. Um, so for controlling, by receiving the command from the DIR pin and setting the number of pulses using PWM from the step pin, the direction could be changed. From the motor controller, the motor driver, V mode and ground were connected to an external power source, since obviously the stepper motors would be working at a higher voltage. Uh, so A4988 driver was used, and for the same board, VDD ground are used to power up the board. Uh, to control the motion of the motor, uh, two XBs are utilized, and this entire communication takes place using UART. Next slide, please. So this flowchart explains the flow of the functioning of the entire project. So what we do is we start at a point we get data from the PC. Um First, the option is to choose the direction. If we choose the direction, we then get to decide whether we want to rotate it in counterclockwise direction or clockwise direction. If we do not want to choose, where it says no, we can move on to angle selection, where based on our choice, there are multiple options like 45 degrees, 90 degrees, and so on. So we can select the angle at which it will rotate. If we select that, we go forward. If not, then we move to the speed. We select the speed of it. Uh, we can either go fast or slow, so it has two modes. Um, in case we want to stop the operation, we can return to the origin and stop the motor completely, and bring it to the original position, which should be set. And the initial position or the origin would be decided by the sensor. Next would be reset. In case we want to reset, we would then reset the motor and reset the entire configuration. The results for the same would be explained by Aniket.
Hello, my name is Aniket, and I will be continuing the results for the module that Abhinav has explained. So, talking about the results, first of all, we'll look at the results for the angle of the motors. So, the Results of the Verilog coding were cross-verified with the university waveforms by the author, and results for different angles were taken, such as 45, 90, 135, etc. As we can see that the stepper motor needs 512 steps uh, to complete an angle of 45 degree. We can see it in the waveform that after 512 steps, the counter register of the motor gets becomes zero, and the enable pin is raised from 0 to 1. This marks the completion of 45 degrees. Similarly, we can see it in the side table that for how many turns and the number of pulses required for various angles. The magnetic sensor detects that the turns are completed and the angle is described. Next slide, please. Now talking about the results for speed, these are taken on an oscilloscope. There are two results for the speed of the motor. The first one shows the slow speed waveform, and its frequency is 34.72 hertz, which is low. And when we see the high speed waveform, that is which is having a frequency of 208.3 hertz, which is very high. So these are the results for the speed of the motor which were taken on an oscilloscope. Next slide, please. Next is the RTL view that was taken from the software after designing the all the module in the software, and this RTL view shows the clock and the input and all the components that are present in the module, and which gives the output in the form of LEDs. Next. Now talking about the conclusion, the prototype is successfully developed in both the areas, hardware and software. The software part is designed using Verilog coding and pulse width modulation. Also, the hardware is designed on a Vera board. The angle, speed, direction, and pause of the stepper motor are included in the design. Next, the controller is also capable of returning the motor to the zero position as the magnetic sensors are used, which detects the motor position and bring it back to the original position that user wants to bring. And the Zigbee transceiver does its work fine and can control the stepper motor wirelessly. So that's it about the controlling of stepper motor using FPGA.